if you want to bring it back to the same temperature, you'll have to remove a certain amount of Q. That tells you how much Q transfer is required for a certain W. So we put in energy as W here. And then if we restore the system to its original state, we require to transfer a certain Q from this system. Now, from observation, we know so now if we apply the first law of thermodynamics, just tells us that Q and W are merely different forms of energy. So so then the first law doesn't prevent the conversion either way. So then we ask this question, what if I try to reverse the process? I supply a certain amount of Q. Will that raise this weight so that I get a certain work output? Now we know from observation that this does not occur. Again, a simpler example. I have one object at high temperature and another at we know that if we bring them together, either direct contact or through a diathermic wall, a certain Q flows. Now, as far as conservation of energy goes, there's no reason why Q cannot flow from low to high temperature. The energy of the lower temperature object, if it decreases, a corresponding increase in the energy of the high temperature object would conserve energy. But we know from observation that this does not occur. So then it seems there is some law in nature which prevents Q from flowing from a lower temperature to a higher temperature and prevents reverse conversion of Q to W. So from these observations, people came up with the second law of thermodynamics. And this has two alternative statements. The Kelvin-Planck statement says So this is based on this thought experiment that you cannot have Q being transferred and being converted completely to work. So the formal statement says that if I have a reservoir at TH and I construct a engine which operates in a cycle, it cannot have QH being transferred and that being completely converted to work. So the Kelvin-Planck statement says that this is not possible. So if this is not possible, what is possible? In practice, you have a lower temperature reservoir and part of QH is converted to work and part of it is rejected to the lower temperature. So without that rejection to a lower temperature, this it says is not possible. So a device which operates in a cycle and just transfers Q from a lower temperature to a higher temperature, this it says is impossible. Okay, so here we have used this idea of something called a thermal reservoir. So what is a thermal reservoir? A thermal reservoir is a body to which or from which heat can be transferred indefinitely without change in the temperature of the reservoir. Thus, a thermal reservoir always remains at constant temperature, the ocean and the atmosphere approach this definition very closely. So it's an object with a very large thermal capacity. So even if you uh, extract a finite amount of thermal energy, or if you transfer a certain amount of thermal energy to it, it doesn't cause a perceptible change in the temperature of the object. So if it's a very large object, so examples of such large objects are the ocean or the atmosphere. So if you transfer a certain amount of Q to the atmosphere is so large, you don't observe a perceptible difference in the temperature of the atmosphere, or say the ocean. Now we have given two statements and we are calling both of them alternative statements of the second law of thermodynamics. So they could be alternative statements of the same law provided they are equivalent. So two statements will be equivalent if either if one statement is correct, the other is also has to be correct. So that applies to both. Or if one statement is false, then the other is also false. So we'll follow the second option. So we'll consider what if the Kelvin-Planck statement is violated. Does it imply that in that case the Clausius will also be violated? And similarly, if the Clausius is violated, does it also imply that the Kelvin-Planck is violated? Let us assume that the Clausius statement is violated. let us say we have two reservoirs at temperatures TH and TL, where by convention we always place the reservoirs according to the temperature. So the higher temperature reservoir is always drawn higher than the lower temperature reservoir. Now, let us say the Clausius statement can be violated. So then I first assume that there is a device which follows the Kelvin-Planck statement. So that has QH transferred to it during a cycle. QL is rejected to the lower temperature reservoir, and W, which is QH minus QL, is the net work output of this device in a cycle. Now, let me consider one more Let me consider one more device which works in a cycle and transfers QL from the lower temperature reservoir to the higher temperature reservoirs. So this violates the Clausius statement. Now, using this, I want to show that I can construct a device which will violate the Kelvin-Planck statement. So then, let me draw a dotted line to enclose this device which was working following the Kelvin-Planck statement, this device which violates the Clausius statement, and also the low temperature reservoir. In that case, since this entire thing is now my device, and I assume this is an assumption which is made in the derivation without being stated very explicitly. Both the statements say for a device operating in a cycle. So then this device operates in a cycle. That cycle has a certain time period. This also operates in a cycle that also has a certain time period. Now, if the two time periods are same, in that case, the entire device also works in a cycle. if the two time periods are not same, if I can take the lowest common multiple of those two time periods, over that time period, all of both the devices complete a certain number of cycles. So then on that period, the entire device works in a cycle, because if it completes a certain number of cycles, it comes back to its original state. So what we require is that device should come back to its original state after the cycle. So what if the two frequencies are not in a their ratio is not a rational number? So that seems a theoretical difficulty, but let's ignore it. So we assume that if I draw a dotted line around this, if both the devices work in a cycle, I can assume that this device also works in a cycle. So this is a device which works in a cycle. Now, since I've included the low temperature reservoir in the device, this device, the device enclosed by the dotted line, this has heat exchange with only one reservoir. So if I see with this high temperature reservoir, the net heat transfer is QH. The net heat transfer is QH minus QL, because I have QH being transferred here and QL being transferred this way. So then if I see the entire device, it is exchanging heat with one reservoir. So QH minus QL is being transferred to this device, and it's doing work which is QH minus QL, which means it is exchanging heat with only one reservoir and converting that completely to work, which is a violation of the Kelvin-Planck statement. So if I assume that I can have a device which violates the Clausius statement, then I can use this in order to cancel the effect of this QL and construct a device which violates the Kelvin-Planck statement. So if I have a device which violates Clausius statement, using that I can construct a device which violates the Kelvin-Planck statement. Now let's try the other way round. So let's say I have a device which follows the Clausius statement that a certain amount of work is required in order to transfer heat from a lower temperature reservoir to a high temperature reservoir. This is what happens in a domestic refrigerator. You have a motor to which you supply electricity, which does work, and that removes Q L from the lower temperature reservoir, since you have put in a certain amount of W, this the heat equivalent of this W together with this together with this QL is rejected as QH to the higher temperature reservoir. Now, let us say I have a device which violates the Kelvin-Planck statement. So then if it violates the Kelvin-Planck statement, it could have heat exchange with one reservoir and that being completely converted to work. Now, so this violates the Kelvin-Planck statement. Now let me consider everything enclosed by the dotted line as the device. So if I do that, then this work from the device which violates the Kelvin-Planck statement is the right amount to supply this W to the refrigerator. So there is no external W being transferred to this device. So whatever the work output of this device which violates the Kelvin-Planck statement is supplied to the device which was operating following the Clausius statement. So there is no work transfer to this device. So then what is the net interaction with the different reservoirs? So this device, since it violates the Kelvin-Planck statement, had a heat exchange with only one reservoir. So there is no exchange with this. So from this reservoir, you are extracting a QL. And then if you see with this reservoir, this device takes QH minus QL. This transfers back QL. So then the upward transfer is QH minus, which is equal to QL. So then in effect, there's no work being done on this device. It is operating in a cycle. It is operating in a cycle and it is transferring QL from the lower temperature reservoir to the higher temperature reservoir. So then we observe that if we have a device which operates in a cycle and violates the Kelvin-Planck statement, then using that I can construct a device which will violate the Clausius statement. So therefore violation of one means violation of the other. So therefore the two statements are equivalent. Now, if you look back, first law of thermodynamics we had first stated it in terms of a cycle, that the cyclic integral of Q and the cyclic integral of W must be the same. Now, using that, we then argued that the difference between the two in a process, not a cycle, must be independent of path. And if it is independent of path, that allows us to define a thermodynamic function, which is the energy. And then the difference in energy between the final and the initial state equals the difference in Q minus the difference Q minus W. So then the second law again we have defined in terms of a cycle, but once again following a method similar to what we followed for the first law. Can we define a physical quantity which is a thermodynamic function which follows from the second law of thermodynamics? It will turn out that such a quantity exists, which is called the entropy. So that is one thing which we need to derive from this, from these statements of the second law of thermodynamics. Apart from that, the second law seems to make a distinction between hotter and colder objects. The zeroth law only told you whether two objects are equally hot or not. But the second law seems to make a distinction between hotter and so whether the two bodies are equally hot or not, that is what the zeroth law told you. If they are not equally hot, which is hotter? Zeroth law doesn't say anything. But here it says, okay, heat transfer is possible without doing any work, provided it occurs from hotter object to a colder object, but not the other way around. So this makes a distinction between a hotter object and a colder object. So then the question arises, can we use the second law in order to provide us a measure of how hot an object is? The motivation for doing that is that earlier we said that while the zeroth law does not tell us how to compare two objects, how hot one is compared to the other if they are not if they are not in thermal equilibrium. So then we said, okay, but then we have to find a way of measuring how hot an object is. And we said, okay, we know that typically objects expand when they are heated. So we can use that, measure the expansion, and use that to determine how hot an object is. But then if we use different substances and try to construct a linear scale between two reference points, then the two materials may not expand in the same manner. So observation showed us that the temperature measured by using expansion of different materials could give us slightly different values for temperatures. So then comes the question, can we from thermodynamics determine a way of measuring temperature? So it turns out that we can define something called a thermodynamic temperature, and that is has no dependence on any material. So it comes directly from the laws of thermodynamics, and therefore is independent of material, and that provides an unambiguous method of defining temperature. But then from the second law, we need to find out a definition of temperature, and we need to define something called entropy. So the first step towards doing that is to define, so far we had been talking vaguely, a device working which operates in a cycle. So in order to make further progress, we need to specifically define a certain device which operates between two reservoirs at different temperatures. So such a cycle is called a Carnot cycle. But before defining that, we need to define something more, the reversible process. Because the Carnot cycle consists of a number of reversible processes. So it says a reversible process for a system is defined as a process that once having taken place can be reversed, and in so doing leave no change in either system or surroundings. So if you carry out a certain process, and if it so the system goes from one state to another, from a state 1 to state 2, if you can bring it back from state 2 back to state 1, and in doing so, not only does the system remain at the same state, but your surroundings are also brought back to the same state, then it's a reversible process. Now, in practice, so if you have a reversible process, you also have irreversible processes. Now, examples of irreversible processes are stirring of a viscous liquid, free expansion of a gas, mixing of two different substances, heat transfer through a finite temperature difference. So this we already know, heat transfer across a finite temperature difference. This is not reversible. It can occur from the higher temperature to a lower temperature, but not the other way around. Similarly, mixing of two different substances, you take you take a chamber, put two different gases, gas A and gas B. So let's say we have a membrane separating them. Then you break this membrane, gas A and gas B mix, and you get a homogeneous mixture of the two if you wait long enough. Now we know from experience that left to itself, two different gases, if you initially start with two different gases in two different zones, they mix, but they do not spontaneously unmix. Similarly, if you have a chamber and you have a partition, you put a gas over here and then puncture this membrane, it will expand and fill this zone, but it does not spontaneously come back. So this free expansion occurs only one way. It doesn't occur the other way. Similarly, stirring of a viscous liquid and a generation of a cube. So the viscous liquid gets heated up when you stir it. And that process cannot be reversed. Now, the Carnot cycle is defined as a process consisting of four reversible processes. So the heat transfer from the reservoirs to the device all occur in isothermal processes. And this is expected because we said all the processes must be reversible, and any heat transfer across a finite temperature gap is irreversible. So during the heat transfer process, the working fluid in the device must remain at the same temperature as the reservoir. So therefore, the heat addition and the heat rejection should both be through isothermal processes. And connecting these isothermal processes are two adiabatic processes which decrease or increase the temperature from the low to the high or the high to the low. So to see it a little more clearly, let's say this is TH. So we have a boiler where QH is transferred to it. So this is the first reversible isothermal process. Then from the boiler, the working fluid goes to a turbine, and this is a typically the hotter fluid from the boiler expands in the turbine and cools down to the temperature of the low temperature reservoir. In the process, it does work. Then from the turbine, it goes to the condenser where it rejects QL to the low temperature reservoir at TL, and from the condenser it goes to a pump which brings it to the temperature of the boiler, and so some work has to be supplied. So this pump is connected to the turbine. So the turbine produces shaft work, part of it drives the pump, and the rest goes as net work output. So this is what a Carnot cycle looks like. Now, the questions which it raises, that how do you have heat addition or heat rejection at constant temperature? That is possible provided there's a phase change. So if there's a phase change, you can add heat without changing temperature. Similarly, if it is condensing, you can it can reject, the working fluid can reject heat without changing temperature. The next question is, how does the pump raise the temperature of the fluid to that of the boiler? In practice, it does not. So that is where the real cycles deviate from this ideal cycle called the Carnot cycle. But then real cycles we'll discuss later. At the moment, we assume that some devices works which some devices available where if you supply work, it will raise the temperature from TL to TH. So this is a heat engine which operates as a Carnot cycle. If you reverse it, then you would get a refrigerator which operates in a reversed Carnot cycle. So this is a heat engine which operates in a Carnot cycle. If you reverse it, it becomes a refrigerator which operates on a reversed Carnot cycle. So let me first take attendance. Okay, so time is over, so we'll stop here. We'll resume in the next class.
Excuse me, Professor.
Yes.
Could you share us the slides of all the lectures to know? Because like obviously we are following the textbooks, but like now that the tests are so close, that would be very helpful.
Actually, I don't know. I always feel that the textbook is a better thing to follow than class notes, because class note is what we are doing right at the moment. There are always chances that we could miss things there, and the total amount of material information available in class notes is limited. Whereas if you go back and read books, that contains more information than what we discussed in class. So that gives you a more complete understanding. So I've been always following this. I can give you, but I've been always following this, that if you had an actual physical class, you don't end up the class, you don't get to carry the blackboard home. So what I'm doing is blackboard work. So I would recommend that you can try to suggest that you try to understand and get an idea from what is discussed in class, because discussion always helps. But then when you go back and read from the book. If you want, I could share it. Um, we can discuss it later. Huh. And I also suggest that just like in a class, you come with notebook and pen. So when you come for these classes, when you attend these classes from home, have notebook and pen ready. So if you want to note down something, you can note it down.
Yes, Professor. Also, Professor, can you please share us the assignment, like some questions related to the concepts that we taught till now?
Okay, I haven't given you any assignments. Now, one student asked this question. So at that time I said, Van Wylen and Sontag, the two chapters, first law, and as he pointed out, I was saying open system. No, the term used there is first law, and first law of thermodynamics, and first law applied to a control volume. So the problems there, why don't you try those?
Yes, Professor. So the syllabus is only those two chapters, right, Professor? Like
Uh,
in
for
Thermo.
this for this class test, that is the syllabus,
Okay.
because that is
Thank you.
what we have been able to do. Okay, in fact, last class I had said that whatever we cover in this week will be the syllabus. So that is
Yes.
still negotiable. Okay. So whatever I'm covering today and tomorrow could also be part of the syllabus. So we'll discuss this tomorrow.
Yeah. Thank you.